Hello community, so great that you are back. Now, in my last video we established that there is no vision reasoning. So I thought in this video we go on vision language AI models and we examine how can we learn them new stuff. And if I say learn, I mean learn and a continuous learning process. Is this possible at all? Let's start. So, I'm here today this weekend at a racetrack and therefore I will explain this new AI research here, by the way, from Google here, live from the racetrack. If you hear something in the background, never mind. But I will also use here, because I'm absolutely focusing on my car, here an example, an analogon from this place here. So imagine you have a stock car. You have a brand new Porsche 911 or a BMW M3. This is here from the dealership. This is here the normal car. Great. Now, on the same side, we have artificial intelligence. Now, we have a pre-trained vision language model, solid, powerful, but rather unspecific, unspecialized, as kind of a foundation model, but not really there yet. So what we do here at the racetrack, this is easy, no? You have multiple tuner here. So you can have a master tuning blueprint and you got here a new tuning chip with secret digital file with all the perfect settings for your car for this particular racetrack here today. So this is great. Well, we can do the same in AI, no problem at all. Maybe it is an AI chip, no? So we take here a LoRa adapter, and this is now the central repo for all our knowledge that we learned so far here on this racetrack from, I don't know, tens, hundreds of rounds here. Now, this is the, if you want, the knowledge that the car learned about the perfect setting. Great. So we have our model, and then we have specific for this task, for this algorithm task here, for this racetrack, a LoRa adapter with everything learned that the car is now perfectly trimmed for this racetrack. But then, you have the idea, what? I want to learn something new on top of everything else. I want to master a new discipline. So you as a professional driver, you hire here a drift specialist, and this drift specialist should create now the ultimate drift setup for your car. Now there's a problem, because here now the complete setup from the general behavior of the car on this particular racetrack and to be a drift car, those will now here have access to the same system parameter in your digital tuning chip. We have the same in AI. If we have an AI system now say, hey, now I have a new task for you AI. I want to train you on some temporary new data, a new downstream task. We have new training data for you. And I want that you become now a specialist vision language adapter model for this new task. And here an example, it is to drift. Great. So we have continuous learning, but the learning now conflicts with the stuff that we already learned. And now what we do, because now we will encounter the danger of a destructive interference. And in both scenarios, because the drift expert will create now their own setup of the car. But it will be brutal only for one task to drift. But I also want to drive on this racetrack and drift on the racetrack. So what you do? Well, the easiest solution is, you just average over the tensor weights of your transformer architecture. In this car, in this element here with the car, it would be the suspension. So you go halfway between a soft one for the road and a rock hard for the drifting exercise. But now your car becomes bouncy and unpredictable because you are somewhere in between. The same if you optimize the differential. You can halfway between open and locked, but this will just fail here in general. So the setup requirements for the two tasks are directly fighting each other because they want to modify the identical weight structure in the transformer layers if we have now the analogon now of the AI training. So this means what we know now for years, almost a decade, we have catastrophic forgetting if we continue learning here vision language model new data. Because simply averaging over the weight structure does not work. It's not just working if you add or concatenate or whatever. You have to come up with a better solution. And this is now the content of this video. So Google developed now, if you want, a new solution, a new paradigm for this and says, hey, We have to have a guided and aligned integration of the new task, of the new learning. You just cannot merge like you want. You just cannot go and somewhere override some tensor structures. We have to have a true fusion process where the new skill not only complements the old one, but makes sure that the old one survive here in our AI architecture. So what do? We define the golden specs. Nobody is allowed to touch them. They are written down. This is on the car, the standard setup. You are not allowed to touch it. And then you can do some testing. Great. You can check for conflicts and you will guide here the learning process. But you have so many other parameters in the car that you can modify. Yeah? So go and modify the other parameters, but don't touch here the golden specs. And it's easy to imagine this, no? You have a base Porsche 911. And then on the racetrack here, you have your chip tuning for this particular racetrack. So you have the car's soul now really shining through on the racetrack. And now you want to do drifting on the racetrack. So this is the new feature we want to learn. This is identical in AI, no? You have a base vision language model. You have learned something for a specific task with an additional LoRa adapter. And then you want to continue learning, no? And for example, you want to learn a new language, a computer language, a human language, whatever. But now, this danger of destructive interference is really the problem. So what we do here on the human side, no? The chief engineer now opens up the master blueprints and tells here the drift expert, hey, listen, buddy, no? They are non-negotiables. No? There are two things you cannot touch, the progressive throttle map here or our stable brake bias here. Never ever come close to my learned parameters. This is it. Your drift setup cannot conflict with these parameters. And the new research by Google called PAM identifies also the most important weight structure in the layers, in the global LoRa adapters. No? So they protect now the core knowledge that defines here the model past successes. It is almost identical. It's almost funny. No? So the drift tuner now remaps here the engine to create a massive instant torque kit, no? For the drifting. You need this, yeah? But the chief engineer comes back and says, listen, buddy, your new settings are the direct opposite of our golden specs for progressive throttle. So they are fighting for the same parameter to modify here the same tensor structure. So what is happening? The boss tells them, hey, revert that one specific setting back to the master specification of the golden rule. Find that instant torque from another source. You have so many other components in the car. You are not allowed to touch here the golden specs. Do a new turbo configuration. Do different timing from wherever you go. Find a solution that aligns with our core feeling of the car here on the racetrack. But you cannot modify the established learning, what happened, what is now encoded here in the learning configuration. And the same happens in AI. No? PAM doesn't just find the conflicts, but if it finds a conflict, the new idea is now to reset the conflicting parameter for the drift here. And this forces now the vision language model or the drift expert here to find an alternative solution. Maybe he will install a new turbo. Maybe he will change the timing of some gadgets in the car. But don't touch what's already learned. And the same is happening here in AI. So you see, of simply blind updates that interfere now with other configuration, no way. No? So we have to train specialists and intelligently merge now their knowledge and their findings into a coherent system configuration. So you guide the learning, you have everything online, beautiful. And the same is happening here in AI. You define here, or Google defined here, the blueprint for continual learning. For an AI system that can evolve gracefully, adding new skills while retaining and building upon its core expertise. Do not override my weight tensors because they represent the learned knowledge. Here we have now the paper, beautiful, 2025, June 5th, just for me, 2 days ago, great, Google DeepMind. And they exactly tackle here what we said, no? Learning here, vision language model, to fight here the catastrophic forgetting that is happening every time we learn here or we add a new adapter here. And they say, hey, for the continual learning, because we want that the system updates and learns continuously, they say we do this here with this new aligned model merging. So instead of fine-tuning, now we merge models that have been fine-tuned before. But we take care that the merging is happening in a controlled environment. Is it working? Here's the result. From the original Google publication I just showed you, here you have the time steps, and on the y-axis you have now the forgetting. Let's say it's in percentage. So if you take one step, great. But if you go with a classical fine-tuning to add a new learning process with new learning data, and we just fine-tune this adapter here on this additional knowledge, you see the old knowledge will be overwritten, let's say 50 is percentage, to a huge amount. So you lose the already learned knowledge, catastrophic forgetting. If you make a copy of the adapter, you go what we just went through together in the last 5 minutes, you find empty spaces here in the tensor space where no huge tensors are created that represent learned knowledge. You find empty spaces in the tensor space. Then you can learn your new task over there. And then you just merge the new virtual tensor structure that you know is an empty space in the master tensor array back, and you see the forgetting is almost neglectable. Now, if you only have a small vision language model and you have a complex task, it is not that easy to find a region where you can work, where you can ignite the learning process on a sub-neural network. Yeah? So you see here, the more time step happen, the more learning happens, comes a little bit down, goes a little bit up in the fine-tuning case, but also the merging is not perfect at all. This is just here at the beginning, but then you say also here, we have a lot of mistakes. And I will show you this in a minute. If we go now to the details, how this merging has happened, you will understand immediately why this is not staying here at a very low level while we are going up, because the method of merging, let me formulate it, is not yet the optimal one. So great. So Google tells us here, hey, look, merging demonstrates a greater robustness to forgetting and task similarity compared just to fine-tuning here a single LoRa module. Great. So let me give you an overview of this. Yeah? So the core challenge that we have now in our continuous learning is we have a dilemma. We have a dilemma between two parameters, the stability and the plasticity of the system. Because we want to learn new things to this vision language model with or without LoRa adapter. So we want to have a high plasticity here, also in the neural network, but without forgetting the old learned knowledge. We want to have the stability. The old learned knowledge is there, is a stable knowledge. So what we do, instead of going now with many separate adapter models, Google tells us now, hey, listen, we have now one central repo for all the knowledge that grows over time. And this is the key to the parameter efficiency of our new vision language model. So we go with a single evolving LoRa adapter structure. And then for each new task, what we do? We take now a copy of this LoRa adapter. We have a temporal LoRa adapter that we now fine-tune on new downstream task. Whatever it is, like drifting, no? So we have it now fine-tuned. It has overwritten something, but we don't allow it that it overwrites wherever it wants, no? Because, as I just showed you, we implement now this process we just went through of a separate temporary expert training that is now isolating here the learning process and prevents here the immediate overwriting of the master knowledge, as we just have went through. So this learning process is now actively monitored, because at each time step, you have to look now at the tensor weights, no? If there's not something happening that is in conflict with the tensor weights that have a high signal, a high magnitude, and therefore you should better not touch them. Those are the golden specifications of already learned knowledge. Find another place, find another subnetwork, find another possibility where you can build in your turbo learning. So you have a continuous monitoring process now. Yeah, and now we go here. How does it really happen? Now, Google tells us where the first sign of a misalignment here, if I want to override maybe a tensor structure, is if those existing tensor and the new tensor that wants to learn now over there, if they have opposite signs. No? Sign plus or minus is a simple but a powerful heuristic, tells us Google, for finding parameters that are working here in direct opposition to each other, causing now a destructive interference. Of course, if you already have there a plus 0.8 and your new learning brings in a minus 0.8, now guess what? It annihilates to nothing. So you lose the learned knowledge and you lose the new knowledge and you have absolutely nothing in your tensor matrix. You don't want that. Now, if you have this conflict, the solution is easy. Google tells us, hey, we reinitialize here the misaligned weight structure. So if you want, this is the core corrective action. It forces the model, hey, not here, not on this tensor. Find an alternative solution pathway that is compatible with the crucial prior knowledge we already encoded here in the neural network. So finding now a solution in a connected low error basin of the loss landscape. So there's so much space here in the tensor space, no? That is maybe not covered here in a dense neural learning network structure. So you have other possibilities. Go and find them. So this guided reinitialization encourages the model now to find a solution for the new task that does not require here large deviation from the parameters important from the old task, from the old encoding in the network. No? So this promotes finding here win-win solutions. First win is you do not touch here the golden specifications of the already learned processes, and win, you can encode a new learning parameter. Yeah, and once a compatible solution is found, the new knowledge is integrated smoothly via merging now of different regions of the tensor space if you want, element-wise. Now you can average, because in the learned tensor, in the huge tensor weight, no? Let's just imagine in a simplification, you have empty region in this tensor space, and now the new learned solution are exactly operative on these new empty regions. So if you merge them, you don't override anything, but you just place new learned functionality into an empty tensor space. And if it works, great. Is it the best solution? No, of course not. It is just the beginning. Because I will show you then later in the critique, we will have a massive compute overhead. So, great. Why we did this? Because the classical model that we just take a simple average merging algorithm here for this, without any alignment that we watch out here, it's absolute suboptimal performance. We have destructive interference. We destroy learned encoded knowledge. So, catastrophic forgetting is happening. This is the standard sequential fine-tuning problem that we face. And Google comes out and says, hey, PAM is here to solve this, at least partially. So when you optimize only for the new task, you destroy performance on the previously learned task. This is not valid anymore, at least not to 100%. So Google are on the right track. Is it a perfect solution? No. If I would not be here on the racetrack, I would be at home. I would have a complete different video. I would show you here, like here in the original paper by Google, that we go here through the matrix manipulation and the matrix multiplication and the tensor structures that we have to build, temporary tensor structures, how we can analyze them, how we can merge them, how we can monitor them, and it would be, 20 minutes here just of matrix and tensor manipulation. I hope you enjoyed the video visualization I've chosen today, but as you see, I was influenced by something else. But otherwise, this is exactly what I told you. This is just a simple LoRa adapter merging operation with a continuous monitoring where the learning is happening. Here you have the pseudocode given by Google. It's exactly the same what we just went through. And I think it's absolutely interesting. This AI is, you can think about AI from almost every perspective. No? Like I told you, you have the classical Porsche 911 here from the dealership. Then you have here the track monster here that has a digital tuning particular now for this track and only for this track here. And then you want to continue learning the AI machine here. And you go to the next level of complexity. You say, I want to have this. I want to keep this performance setup here. But now I want here this additional feature or this additional ability. How can I drift to be even faster here in the bends here? So in the corners. So this is really absolutely fascinating. And we don't know the solution to this. And this is published by Google just 2 days ago for me recording this video. And they are fighting. They don't know how to continuously train their vision language models. For one step, it's great, but then breakdown, catastrophic forgetting. So absolutely fascinating to see here the published solution by the global corporations. Am I allowed to critique a Google paper? Yes, of course I am allowed. So let's start. What is it that I'm focusing on? You know, this is the statement. They tell us here the modification of the conventional learning paradigm is rather simple. Fine-tuning a temporary copy of the LoRa module on the new task and then merging here the learned parameters into a separable global LoRa module that evolves over time. Okay. But if we only use here a simple and effective heuristic, I think this is not enough. So if we go here for the weights of the highest magnitude, and we have a threshold tau to include only the top, 50%, I don't think this is correct. I mean, I see this as a major part. If you think about this as an iterative step, yes, absolutely in the right direction, but this is not the final solution. Eh? Because you can't say that only the top 50% of the highest magnitude weight tensors represent the most critical knowledge from the past task that I have to conserve. Because, yeah, you get it, yeah? And what's also nice, before fine-tuning now the temporary copied adapter here on the new task, they do now this, what they call magic here, and they perform the alignment check. Would I use tensors that are already encoded here from old knowledge? And then, simple solution, reinitialize the weight in the copied tensors and find another solution. So I think it's more of a trial and error approach, né? Because, let's be honest, the sign or the sheer magnitude of a single weight tensor in a dense neural network of multiple layers, it is not here the singular decision criterion. Can I use this or not? Am I allowed to write there or not? And the complexity of general information encoded in any neural structure, network architecture, I don't think you can ignore this just because it is below a magnitude threshold, you know? I think we can encode knowledge in a real complex neural structure also without having spikes, with dominant spikes here. I think you can have low magnitude activations in our network, and they also encode very important knowledge. So to ignore those, I don't think that this is a solution. And you see in the performance data, if we go to higher time steps, this merging is not working anymore as we expect it to do. Right? And if we have to do a continual monitoring, this is fine for very tiny vision language models. But imagine you would do this on an R1 with 671 billion free trainable parameter. And you would, during the training, now monitor here the tensor weight structures. Now, in real time. I mean, if you Google, you say, okay, 1000 TPU chips, no problem at all. But if you are a normal person living here on this beautiful planet, yeah, I think this is this is the very first step. Okay, we're approaching a solution here, but I think this cannot be the final solution for learning here, because this will just generate massive compute overhead. So there's a solution waiting outside. I hope you find a solution. I hope you have the time at this weekend to sit down and enjoy this beautiful publication by Google. Have a look. There are a lot of numerical data. There are a lot of ablation studies and additional data. It's really fascinating to see we have not solved the most basic principle problems. How can we make or build a system that is able to learn at least 3 steps, 3 new continuous tasks. It is still catastrophic forgetting. We still override the learned knowledge. And you see, Google shows us this and says, hey, maybe we found here the beginning of a solution. I hope you enjoyed it. I hope you have a great weekend. I see you then next week. If you subscribe, would be great.